So a few videos ago, I talked about this concept, the AI verification problem. And in order to kind of expound on this even more, I have to explain this idea of inductive computing, which is my own term that I use to call AI or LLMs. But in fact, it falls for all sort of machine learning tools. What do I mean by this term, inductive computing? And you might have heard me use this. I used this in the video a few videos back. But to understand what this means, we need to think about what deductive computing would look like, and also think about the difference between deductive and inductive reasoning. So just to begin, deductive reasoning is the kind of logical reasoning you learn in your basic computer science courses, with your rules for taking your logical ands, your logical ors, you have your material implications and these sorts of things, negation. So when you're performing deductive reasoning, you start from a set of assumptions, okay? These are called your axioms or proposition. And then you apply various deductive rules to reach the conclusion. And usually the types of deductive rules we use is what's called natural deduction. Okay, and there's some natural deduction systems. And of course, there's a whole bunch of other proof types and different deductive rules that you can apply and this sort of thing. But the point is, you start with axioms, you have a bunch of rules, and you arrive to the conclusions by just applying the rules to these axioms. Inductive reasoning, on the other hand, is more observational. So what do I mean by this? You receive an observation. When I drop this thing, it falls. Okay, it falls downward. When I drop another thing, I drop an apple, it falls. I drop a banana, it falls. Okay, and based on this observation, I reach a conclusion, and that's that all fruits will fall when I drop them. Question now is, okay, well, why is this different? And the point is, when I'm doing inductive reasoning, I am creating a hypothesis based on evidence. Okay, or really what I'm doing is I'm arriving to a conclusion based on observed evidence and the application of some inductive inference rule. Right? So usually this rule looks, a lot of the time, this rule looks something like things that have occurred in the past will occur in the future. This is kind of like the most basic inductive rule we can apply. And there's different kinds. There's Bayesian inference, which is a kind of inductive rule as well. But the point is, we have some sort of inductive rule that we apply to observed evidence, and we get this conclusion. Then the next thing that kind of falls in line here is this idea of modalities. So even though a statement can be true, there's different ways in which it can be true. And so the main one that we in logic call is, and so in logic we have this concept called modal logics, and these contain a concept of necessarily true and probably true. Okay, and they're connected in certain ways, which I'm not going to get into the specifics of modal logic here. But the point is, when I have a truth statement, I can kind of apply a modality to it and say, oh, this is necessarily true, which means that you can kind of imagine that it'll be true in like every kind of interpretation. But a statement is probably true if we can't say that it is true in every interpretation, if that makes sense. And so why this is important is that when you're talking about a deductive reasoning step, these are always necessarily true. Okay, so if I get my axioms and I arrive to my conclusion, that is necessarily true. It's necessarily true that if I start with these inputs, I will get these outputs. Versus in inductive reasoning, the best we can really say is that the conclusion is probably true, right? Because we could, unless we've observed every possible instance of every possible observation ever to draw this conclusion, we don't have knowledge if there exists a piece of evidence which will disprove the conclusion that we just haven't observed yet. So this is the problem. It's not exactly a problem. This kind of comes with its own kind of baggage here, where it's like, okay, we can keep this necessary truth, but then it requires us to have proper axioms and a bunch of deductive rules, or we can be okay with probably truths, and then just have an update rule and just collect good enough evidence. These are kind of two ways of doing reasoning. And maybe you can see, something like psychology is a bit more in that inductive realm, something like mathematics is more deductive. Let's go all the way back to computing, because it's a bit of a tangent. So classically, computing is very deductive. And what I mean is, when you write an algorithm, okay, your algorithm, as long as it compiles, is effectively correct, in the sense that if I give you certain inputs, I will always get that same output, and I can prove it using various rules, right? And that's because programming languages are written very formally, right? They are formal, they have like a formal logical syntax where the compiler is able to reason through these things. And of course, you can get weird bugs where this doesn't work. It's just like, there's like mutation and you have state that exists outside of a function's block of memory that can be done, and this sorts of stuff, right? But in theory, okay, if you keep the beginning inputs the same, then when that code runs, you're going to get the same output. And this will be true for all machine learning algorithms. When we try to do computation with machine learning algorithms, the best we can do is take a bunch of observations, and this is just the training data. Okay, then you arrive to a conclusion, and you arrive to that conclusion using some inductive inference rule. What is that inductive inference rule? It's the training step. It's that, it's the sort of mathematical equations you perform to do the training. And the thing is, you can't say that the model is correct. Like if I gave you a piece of code, I can tell you, yes, this is correct. This code is correct. It'll provide the correct input, or yes, this code is correct. It'll provide the correct output on the correct input. But I can't say that for something like a machine learning model, because it's not fundamentally deductive, it's inductive, right? The answer is probably correct, but I don't know if there is some situation that is some out of sample situation where the answer is wildly different from what the model predicts. I don't know that. And if I find that outlier, I add it into training set and try to sort of fix the model and this sort of thing. But like, this is that inductive process. And so this is where I get to the part where I say that AI, inductive computing, because, well, it's a computational task, and it is really a computational task that can only be done inductively. And there is a sense in which this kind of is deductive. Effectively, if I keep everything the same, I have the same training data, okay, and I use the same random seeds in the model for the weightings and all this sort of stuff, and then I train it on the same data set, same rate, same weightings, two different models, I'll get the same model, right? The thing is, the performance, like how it works, or the performance, like the sort of program that I've created is inductive. It is an inductive program. I can't prove that it runs correctly. I can only assume it runs correctly because I have an inductive, through some inductive inference rule, and that inductive inference rule is that I've trained it. And so think about that. Like, anytime someone tells you that AI is going to solve all these problems, just think about that the AI will never be able to necessarily solve a problem. It can only, at best, probably solve a problem, just because fundamentally AI systems are inductive, not deductive. Now, I'm not trying to say that this is a problem one way or the other, that everything has to be deductive and that you can never do things inductively, right? But if you care about the quality of certain code, or if you care about truth in a way, like provability, then inductive computing is just sort of a thing you can't really do, because you don't have that, because fundamentally it's just not built into induction, right? And maybe you have this idea. It's like, oh, well, what if you found a way to have a sort of a deductive explanation for induction? Well, then if you could do that, you could solve Hume's problem of induction, which has been plaguing philosophers for centuries, right? So if you think you can do that, go right ahead, be my guest. But so far, no one's really done it. All right, so that's it for me this time. If you have an interesting topic idea, I'd definitely send a comment, like and subscribe so that more people see this video. And I'll see you all in the next one.